G'day guys, and welcome to our lesson on electromagnetic induction, or how to induce current in a wire. To summarize what we know so far, we looked at magnets, which are dipoles. They have a north and south pole. And we looked at how they produce these magnetic field lines. Well, they produce a magnetic field, which we can model with this magnetic field line diagram. And the lines point away from the North Pole and towards the South Pole, except inside the magnet where they tend to point towards the North Pole. These lines show the direction the north face of a compass needle would point, so the North Pole of a compass needle would point, if it were placed at that location. We also said it was a vector. This magnetic field line, or a magnetic field was a vector, it's B there. And we said it was stronger closer to the magnet. Our explanation for that was that the lines got closer together here, but over here they were far apart. So B is a measure of both the direction and the strength. And the unit of B here is Tesla. So I'll put that in brackets down here, Teslas. We then looked at how when a charge is moving, when a charge is moving along a wire through a magnetic field, actually we'll start with just the charge. The charge moving on a wire along a magnetic field, if the electrons are flowing this way, the positive charge is implicitly flowing that way. This moving charge will generate an electric field. And we use the right hand grip rule. So we put our thumb of our right hand along the direction the current is flowing. And then we curl our fingers around that wire. And the direction our fingers are curling shows us the direction of the magnetic field lines. So the fingers are pointing towards us there. And if that hand were to rotate around, we'd have magnetic field lines going into the page. We then looked at what I was just about to draw before. If you already had a magnetic field present, so this magnetic field is not caused by the current in this wire, it's already there, it's independent, this wire will experience a force, and that was the force is equal to N BIL. Now I include the N in here because it's very easy to remember the N if you learn the formula this way, but it gets trickier to remember it if you normally learn it without the N. So if you just learn F equals BIL, I prefer F equals NBIL, and if it's a single wire, N will be 1. If it's a bunch of wires, you choose the value of N that's appropriate. So to find the force on this wire, we use the right hand slap rule, which is put your thumb in the direction of the current. You put your fingers in the direction of the magnetic field, which is going into the page here. So those fingers will basically just disappear over there. And the direction your palm faces shows the direction of the force. So it's straight up there. Always remember to use your right hand for these rules. Right hand grip, right hand slap. If you use your left hand, you'll end up with a force going the wrong way. So what are we covering now? Electromagnetic induction. Say we have a loop of wire, and that loop of wire exists in a magnetic field. So it's got no current through it, it's just sitting there. And then, if I remove this magnetic field, we would see a current start to pass through that wire. And that current would be flowing in this direction here. Let's see why that is. So we'll make the loop of wire square. We'll have its side length 2 meters. And we'll say initially it has no flux, no magnetic field. If we were to then, over 3 seconds, bump up the strength of this magnetic field. So suddenly it's coming out of the page here. So that B, the magnetic field, the strength of the magnetic field, were equal to 3 Tesla, we would again see a current through this square loop. So a current would begin to flow. And I believe the current would flow in that direction there. Let's see why that is. First of all, recognize the concept of flux. It's basically a count of the number of magnetic field lines passing through an area. This is our area in here. The area is equal to 2 meters times 2 meters, 4 square meters. And we find the flux by multiplying the magnetic field strength, or we say the magnetic field line density, which is B, which is 3 Tesla, by the area, 4 meters squared. And we get 12 Tesla meters squared, or more commonly, 12 Webers. So that's the final flux we had. Flux final. But remember, the initial flux, when there was no magnetic field inside or out, must have been equal to BA, so 0 times the area, that's 0. So there was a change in flux, given by the final flux take away the initial flux, and that would be 12 take 0, or 12 Webers change. So the flux through this loop here has changed when we change that magnetic field. We've also had a change in time, t equals 3 seconds, an instantaneous change in flux. I'm not sure if that's even possible. I mean, a very large instantaneous change in flux. It's a bit like acceleration or change in velocity. You know, to change velocity, you need a little bit of time to do it in. So we've got 3 seconds over which this happened. And to calculate the voltage going around this loop here, forget about the direction for now, we use the voltage, EMF, is equal to N, there's only one Y here, times delta phi, which is 12 Webers, over delta T, which is 3. So we get 4 volts of EMF. Now the direction, we use Lenz's law, Lenz's law. I will say Lenz's law, which states a current will be induced which will oppose the change in flux. So the loop will experience a current through it, which will hopefully, I like to think, make things the way they used to be. So we start off with 0 flux going through. Then all of a sudden a magnetic field comes out of the page towards us. The flux has increased towards us. So a current will pass through this wire to return the flux to nothing. And the way to do that, if you put your thumb along the wire there, and you want to oppose this change in flux, you want to put flux in the opposite direction. So you want to have flux going like that. So if we put our thumb in that direction, we'll find our fingers are pointing into the page there, away from us, and that will achieve our desired opposition to that change in flux there. If we had the current flowing in the opposite direction, with our fingers now curling up towards us, that would in fact be helping the change in flux. We're adding to the number of magnetic field lines coming towards us there. So you don't want the current to flow in that direction, but rather, as we had before, if you want to oppose that change in flux, you want the current flowing in that direction there. So 0 flux, flux starts to come out, the current says, hey, enough of that, starts flowing around in that direction, and hopefully pushes magnetic field lines into the page, resulting in a net magnetic field of 0. But of course that never happens. The magnetic field that's being induced tends to win. The only exception being, I think you call it a perfect conductor, which is the type of thing you'd want to use in a maglev train. Let's try another example. Sometimes the magnetic field doesn't have to change and the area doesn't have to change, but the orientation of the loop does change. So we'll have a look at that. Say I've got magnetic field going across the page there, and then a loop facing us, but it's on this axle here. The loop has a diameter of 10 centimeters or 0.1 meters. The strength of the magnetic field is equal to 0.5 Tesla. And the number of wires in this loop is 1. We say loop generally means 1 wire. If this loop was suddenly turned 90 degrees, so side on it would look like that now, if it were turned like that around. Let's calculate the amount of flux. Let's calculate the total EMF that would be generated. We'll calculate the flux on the way. So first, what is the initial flux? And we'll say also that took place over how many seconds? We'll say 3 seconds. The initial flux, well, if this loop really is side on to the magnetic field, then these field lines here are unable to pass through the loop at all. They're passing along the plane of the loop. So the first thing you've got to realize is that flux depends on at least some field lines passing through the loop. Another way of describing it is that flux, I've written B times A here, but it's more correct to say B dot A, which is equal to the magnitude of B times the magnitude of A multiplied by the sine of the angle between them. If they are parallel, the angle here is 0, so sine theta is equal to 0, and we have no flux at all. If the area is parallel to the magnetic field lines, you don't get any flux. So the initial flux is 0. The final flux is equal to, when it's turned 90 degrees, the area is exactly at right angles to those magnetic field lines. So we're going to get the most amount of magnetic field lines passing through that loop as possible. So flux is equal to B times A at 90 degrees, which is equal to 0.5, and the area of this loop is pi r squared. So that's pi, and r is 0.05 meters. Always dealing in meters, seconds, kilograms, that sort of thing, to keep our formulas working well. And this I have coming to 0.5 times pi times 0.05 squared I have 0.00393. And the time it took is t. So to find the delta flux, we say it's delta final, take delta initial. So that's 0.00393. And if we divide that by delta time, that's divided by 3. And I have that coming to 0.00, of course n equals 1 also, 0.00131 volts, or 1.31 millivolts. So not a lot of voltage generated in this wire. We found the magnitude. Let's find the direction. So this loop's enjoying itself, having no flux, and then we disturb it by shifting it around like that. So it's at right angles. So it's turning that way there, that arrow going into the background. It will suddenly experience, coming in from the back side of this loop, a lot of flux increase. And it'll want to decrease that amount of flux. So just drawing that again, this side will move towards us and that side will move further away. If it wants to decrease the flux coming in from behind it, we run our right thumb along there and we curl our fingers away from us. It'll start pumping field lines like that, because as this swings around, those field lines will actually oppose the field lines that are running from left to right there. So using our right hand grip rule, we see the current will flow in that direction there. If we were to turn the loop the other way, we'd expect the current to flow in the opposite direction. Yes, in the opposite direction. Sometimes you can verify it visually if you imagine your hand sitting on that wire. The last thing I want to show you is if I had a graph. This is very maths methods. And we had a graph of the flux and the time here. The EMF is equal to N. We'll say it's a loop, so N equals 1 here. Delta flux over delta time. Delta flux over delta time is the gradient, the change in flux over the change in time, the gradient of this graph here. So if I drew the flux graph, like that, and then I shrunk that down, moved it up, copied, pasted it, moved it down, erased the original graph, and now I've decided to draw the voltage below it. The voltage, the EMF, is going to equal the gradient of this graph, the gradient function we'd say. So here the gradient is quite large. Here the gradient becomes 0. Whoops, voltage, large, 0. Here the gradient is quite negative. Here the gradient is 0. Here the gradient is positive. And then here it's approaching 0 again. So my voltage is going to look something like this. This tends to be what you see when you spin a coil in a power generator. We'll look at that in the power generation video.